Hey everyone. Looks like it's 11:05, so I think most people who are going to come have already come. If a few people trickle in, the first couple slides are agenda, so we'll let them come in. But we're going to start right about now. Cool. So this is the latest in our Markforged webinar series. This webinar is talking about fiber filling techniques. So this is a little bit more of an advanced webinar towards working with our printers to make the strongest parts. I'm Daniel Young. I'm an application engineer here, and we also have with me Alex Crease, who's also an application engineer, and he'll be answering questions through the question portal as well as helping me out after the presentation. Just an idea of structure, the presentation will probably go about 20 minutes, and then the rest of the time will be devoted to questions. We're scheduled until noon. We can go longer if we absolutely need to. We also can go shorter if there's no one else that needs to ask questions. Awesome. So we'll get started. So first, a really quick agenda. We're going to start because we have a lot of new people signed up for this webinar that don't know a lot about Markforged. We're going to start with a very brief introduction. Then we're going to go into the raw options with fiber filling, so what you can actually do in terms of fill options and specific things. And then we're going to go into a few strategies that we like using when we're filling fiber in-house, and what we generally tell our anyone who asks us for help. So first, a very brief introduction to Markforged. Markforged makes 3D printers, software, and materials. We make a closed-loop system, and our whole goal is to print stronger. So all of the machines we make are engineered to print parts as strong as possible. We have our product line starts at $3,500 with a printer that prints with no continuous fiber. It just prints with chopped carbon fiber. And those parts are stiff, but they're not particularly strong. And then as you go further up our product line, we get to what our hallmark is, which is continuous fiber. This fiber is ironed down layer by layer in parts and makes parts incredibly strong in 2.5 axes. So that fiber that we're talking about here is what we'll be discussing in the webinar, and hopefully this will be kind of a deep dive and this is an introduction to people who haven't seen it yet. So first, why is fiber so important? So on the left side of the screen we have great design, which hopefully most people who use our machines have, and on the right side we have strong part. With metal and with a lot of other things, it's really not hard to get from these. The arrow is just fabrication. But for us, there's smart fiber usage. And so what that really means is once you have a part that's designed well, you still have more work to do in our software to make sure that there's a strong part that comes off the printer. Now, granted, this work is not impossible or even hard, but it is something that you need to be cognizant of when you're working with our machines. So this webinar is kind of teaching you how to use fiber in an intelligent way. So first, the bare bone basics of fiber fill. So we have two options at the highest level with fiber fill. We have concentric fiber and isotropic fiber. So concentric fiber, which is the one that we use more often than not, is a default where we start from one location on the print, whether it be the outside, the inside, or both, and we start looping fiber around the part until either the specified number of loops is met or until we can't anymore. So if you look at this part, this is a bike pedal crankshaft. Crank, and you can see that it has fiber on the left side looping around constantly. Isotropic is slightly different. With isotropic, we start with a concentric loop around the outside of the part, but once we finish with that loop, what we do is we do zigzags. And so these zigzagging layers, I don't know if the stream is good enough, but this thing on the left is actually a GIF where you can see that these zigzags are alternating by 45 degrees every layer. So these parts are a lot stronger. However, they don't print they take longer to print. They're more expensive to print, and they don't generally print as well. But what they do give you is multi-directional fiber strength that you can specify. So our default on these is that you can go from 45 to 90 to 135 to 180 in terms of rotation of the fiber. But you can actually specify whatever you want. So isotropic really gives you the option to customize the direction of your fiber in parts. So now a little bit deeper into what you can do with concentric and isotropic, just at the top level. So the first thing is concentric has 3 options. This is actually a feature that we launched about 2 weeks ago. So this is a pretty new thing that people have been asking for a long time. So the first is outer shell, which is the top left option here. And what that is, as I mentioned, it starts from the outside and loops in the specified number of layers. So For all three of these examples, what this is set to is concentric fiber and then 3 rings. So if you look at the outer shell on that one, you can see there's 3 rings of fiber looping in from the outside inward. Then if we move over to the top right, we have his inner holes. So this takes all of the holes that it can reinforce. It's important to note here that those 4 bolt holes on the outer parts of the crank can't be reinforced because they're too thin, but we'll get into that in a second. And with this inner hole that it can reinforce for the crank, it starts on the middle and takes 3 loops outward. And so that does is it helps you if you'd rather have the inside of the part actually reinforced than the outside, then you can do that. So that's a new option. The other new option that we have is all walls. All walls is simply a combination of both of them. So this is again 3 loops. So what it'll do is it'll start on the outside, do 3 loops, and then start on any inner holes and do 3 loops. One thing to note is that if your holes are very close together, we have some interesting edge cases that we're still working through. Because let's say you require three loops of fiber around 2 holes that can't fit 3 loops in between. It won't always reinforce. So it's important to look inside internal view, which we'll get into again a little bit later, and discuss what you can do with those cases. So now with isotropic, I mentioned one of the things you can do with isotropic, which is determine the rotation of the actual the main line of the zigzag. So that's one of the things. The other thing you can do is specify the number of rings that you put around the part. So if you look on the right part, the right part has one, or sorry, the left part. The left part has 1 concentric ring on the outside and inside that are bounding the zigzags. And so what that allows is the maximum amount of actual isotropically laid fiber to fit in. It does, when you have something that has fewer shells, you run the risk of having less a poorer surface finish because isotropic tends to lend itself to that, but it will get you more fiber. So the other thing you can do is add more rings. So on this other one, I just added 3 and then fit isotropic. But the big caveat here is that since fiber can only fit in a specific space, you end up with fiber gaps inside this part. So the part that has fewer rings actually has more fiber in the part. And again, these are all things that you can predict, but are kind of best measured by going into a part after you've laid it out and just checking it in internal view. So now that we've kind of been talking about the 2 options here, a couple key limitations. So on the left, we have the minimum thickness for 1 strand of fiber. So this is a pretty commonly asked question: is can I fit fiber here, or why can't I fit fiber here? So the minimum thickness for 1 strand of fiber is 2.9 millimeters. So that means that if you have a ring or something like this, you need a thickness of 2.9 millimeters to fit 1 strand of fiber. And then the minimum thickness for 2 strands, so a loop, is 3.8. So this is really important if you're making a turbine or something that requires you to have sort of an extended set of loop of fiber, because it will not put 1 strand in that. It requires a loop. So these 2 are very rectangular options. So these are kind of it will fit or it won't. It's also important to examine these limitations in a more realistic sense. And so for that, we've kind of shown a gear. So the left gear is twice as large as the right gear. So if you look at the left gear, when we put 2 loops of fiber in it, the fiber fills the whole tooth of the gear all the way to the end of the tooth. For an application like this, that's pretty important because gears suffer from a lot of contact loading, and you really don't want a tooth. You want a tooth to be as strong as possible through the whole tooth. If we look at the scaled down version on the other side here, the fiber again fits in the tooth of the gear upon like a cursory look. But if you look closer, it really only reaches the pitch circle of the gear. So it's really important to look at the internal view again after you've laid out fiber to make sure that when you're laying it out, it's actually getting as far as you want. Now, that's not to say that this gear on the right would not work, but it is certainly less likely to work because there's less fiber that can fit. And from like a technical perspective, the reason it's not fitting is because that 3.8 millimeters has that barrier has been broken as the gear narrows towards the end. Whereas on the other one, the gear is at least that thickness throughout the whole length of the tooth, and what that means is that it can fit fiber. So that's kind of the end of our basic sections. Those are just constraints and what you can do on a bare bones level. So now we're going to go into a few of these fiber fill strategies. So Alex and I are both application engineers here, which means we make a lot of sample parts and parts that are proofs of concept and work with people on support to make parts. And so generally about 90–95% of the time, when we're suggesting fiber fill, it will be in one of these following strategies that are kind of macro level applications of what we've just taught before. So the first one is sandwich paneling. So this is the default that we have on our software. So if you go into iGrow, our software, and click turn fiber to on, it will default to sandwich paneling with concentric rings of fiber and just a few layers. And so what sandwich paneling does is it puts layers of fiber on the top and bottom of the part as low and as high as it can possibly get. So once the roofs and the floors of the part are printed, it'll print those layers of fiber. So this is really good for bending about one axis, but it's not really good for anything else. The thing is that it will make parts strong for very little fiber. So from a cost perspective, it's very good. So sandwich paneling, while very rudimentary, is again like a very useful way to use fiber and save a lot of money, because it's very easy for fiber prices to go up. With fiber prices high, it's very easy for your part price to go up as you use more and more fiber. So this is a very fiber efficient way to get some strength out of your part. There's one caveat with the default and so a lot of people when we're working with our software, when they'll just click fiber and then click print. And so there's one issue, and that is that it, especially with top layers, it will put fiber in the topmost layer that it can possibly put. So I'm playing a video through PowerPoint right now. I'm not sure if it's, we've had some troubles with them working well in the past, but basically what we're showing here is that with this brake lever, there's a rib on the top of the part that constitutes the top layers of the part. So when our software goes in and tries to put fiber in, on the bottom it'll put fiber in the correct spot, but on the top it will only attempt to put fiber on that tiny embossed ring on the top right of the part that it's showing right now. And so what that means is that you're not actually getting strength in the top of the part. So there's actually a pretty easy workaround to this, which was shown in that video, which I'll try to play again. Oh, shoot. Sorry. All right, the video is not quite playing. But basically what we do in this is that we then shift the fiber down to make sure it's actually in the top part of the body of the part, as opposed to being in that ring. We can discuss this more in questions, because that video didn't quite play quite right, but that's the gist of that for now. So the next one is shelling. So if you're trying to get a strong part for as little fiber as you possibly can, and by strong I mean unidirectionally strong, this is honestly the best way you can go. This is how we make all of our brake lever sample parts. So if you've seen one of those, they're kind of our larger ones. Pretty much all of them are filled with this fiber strategy. So what you're doing with this is you're using a sandwich panel on the top and bottom, which will give you that strength about that one axis, and then you're using a shell of like 1 or 2 concentric ring shell around the outside of the rest of the part. So you have 3 different fiber fill regimes. So on the top and the bottom of the part, you have your sandwich panel. And with this sandwich panel, it doesn't really matter if it's concentric or isotropic. It can be either. And with the middle section of the part, you only have 1 or 2 rings, but you have concentric throughout. And so what that gives you is a shell of fiber around the part. And so that means that your part's really going to be strong in almost any dimension. The one caveat is you're still not going to have great z-axis strength in tension, but with torsion and with bending about almost any axis, this part will be... All right. Looks like we're back online. Sorry about that, guys. Apparently GoToWebinar didn't really want us to finish sharing our fiber strategies today. So I'm going to go back one slide and just continue the presentation as is. So back to shelling. As we were kind of discussing before, I'm not sure when we got disconnected, but what shelling is you're putting fiber around the outsides of the part, and the way you're doing that is you're using sandwich panels on the top and bottom that can either be concentric or isotropic fill, and they're using 1 or 2 rings of concentric fiber around the outside of the rest of the part. So if you look at this histogram on the bottom of the part that I'm kind of pointing to with my cursor, you can see there's 3 regimes of fiber. There's 2 on the edges of the histogram, which represent the top and the bottom of the part, where there's lots of fiber. So those are the sandwich panels. And then there's just, like, for the rest of the part, there's a separate regime that has just a little bit of fiber, and that's where the shell is. So now we're going to move back onto striping. So I think this is when it cut out, just about when it cut out. So if you look at this, this is a 3-dimensional view of that same crankshaft. and you have three different regimes of fiber. You have the two on the top and bottom that are the basic sandwich panel, and then you have the third in the middle, which is currently being clicked on in the video, which is just an extra section of fiber in the middle. Sandwich paneling is often done with isotropic fiber, but you can again do it with either. It just matters that you put a significant amount of fiber in that area of the part. The advantages of striping are twofold. One, if you want to increase the torsional stability of your part for very little fiber, this is one of the best ways to do it. And second, if you're trying to reinforce a specific few layers of the part, so the example I was getting into, I think, when it cut out, was that we got another Ducati in that we were designing a brake lever for, and this one in particular had a couple of small flanges in the middle of the part, and we wanted to reinforce those flanges specifically. So we used a striping technique to reinforce those areas specifically within the part without wasting too much fiber on the rest of the part. Cool. All right, so the next one that we really that you can do, but we don't honestly recommend, is full fiber. So this, again, you can use concentric or isotropic. This is probably the simplest one. Basically, what you do is you either use isotropic fill for every layer of the part, or use concentric fill and up the number of layers as much as possible till the limit is not the number of layers that you've specified, but instead the amount of fiber it can physically fit in the part. This is good if you really, really want an extremely stiff part, or if you want a really heavy part. However, our fiber is not cheap, so if you're attempting to get the best value out of the printer, this is probably not your best option. The other thing is that when fiber generally decreases the likelihood of you getting a good print with good surface finish and good quality. When you put very little fiber, the amount it decreases is negligible. But if you fill the whole part with fiber, there's a non-zero chance that the part will fail because of just the sheer amount of fiber inside of it. And again, we generally think of this strategy as more overkill than anything else, but there are a few applications where it's necessary. We've been working on, as application engineers, we were working on a demo part that was a pipe wrench, and we used full fiber for that. But again, that's kind of an edge case and more of a demonstration than anything else. So again, this is something you can do, but not something that we ever really recommend. All right, cool. And so those are the main strategies that we talk about. Honestly, the ones we use most are probably sandwich paneling and shelling, just as a default. They're kind of the best ones for your bang for your buck cost-wise. With party notes, we have don't overuse fiber. Fiber is very, very useful for strength, and it's very, very light, but it's also expensive. So it costs a lot of money to put a lot of fiber in your part, and it's kind of a law of diminishing returns with the amount of strength you'll get out of it. So that's kind of an important thing to talk about. And also check the internal view. So this wasn't really an Eiger-focused webinar, although we kind of looked at Eiger a fair amount. So when you slice a part, you can just slice a part with fiber in it and click print, but that's really not the best strategy. Well, it might save you a little bit of time. It's probably going to cost you more in the fact that the part may or may not come out well. So once you finish slicing a part with fiber in it, you really want to make sure you check the internal view and ensure that the fiber is actually doing what you want. And the second is to use both the three-dimensional and the two-dimensional view. So we kind of touched on that a little bit. The three-dimensional view is visible in all of those videos that we're showing about specific fiber filling strategies. And so the three-dimensional view will show you, it'll show you groups of fiber. So it'll show you specifically where you have those, and you can click on them and navigate there. But what it won't show you is layer by layer. And so that's where a 2D view really comes into handy. So if you want to see what the fiber is doing for a specific layer of the part, that's a very, very useful strategy. All right, so that's all we have in the formal presentation. But as we said before, we'll open up to questions, and we'll answer all the questions as best we can. So it looks like we opened up with 2 questions. Alex will kind of feed the questions if we have them. The first couple of questions are, one, can we put fiber on the outside of parts? The outsides of our parts always are the thermoplastic nylon that we use. So on the outside of the part, no, but you can put fiber very, very close to the edge. I think that what you may be getting at here is related to surface hardness. Our parts are still plastic on the outside. They're tough, but we wouldn't really describe them as having anything comparable to metal in terms of surface hardness. So yeah, that's the answer there. And then the other one is, can you reinforce only specific sections of a part? So right now, in terms of specific sections, no, you can't call out a specific section, but what you can do is you can navigate the tools we kind of just showed and reinforce only areas. So if I want to reinforce only the outside or the inside of the part, I can specify that now, but I can't say that I only want to reinforce one hole. Cool. And now the questions are coming in. So what is the minimum length of fiber? On the Mark 1, the minimum length is really long. Right now, I think so the fiber cutter is on the head now. That was the biggest design upgrade that we made. And so the minimum length of fiber is pretty negligible. I want to say it's about 1.5 inches. Does that make sense, Alex? Yeah.
40 millimeters.
Yeah. What, 40?
40 millimeters.
Yeah, so 40 millimeters, which is about the same. So can we go back to the fitting fiber in small areas again? Yes, the gear. Okay, so there's a few questions about fitting fiber. So printing a part that was 2.9 millimeters did not put a strand of fiber in it. Can you force it to put a single strand in? The answer is no to that. It has to be a loop. That's just how it works. So the 2.9 millimeters only works if you have a ring that's 2.59 millimeters, not a single length. If it's a single length part, it has to be 3.8. So I'm going to go back. Someone asked to explain the gear example again, so I'm going to go back to that quickly. Okay, there it is. So if you look here at this gear example, again, the left gear is twice as large as the right gear. So if you look at the left gear, the fiber reaches all the way to the edge of the tooth, whereas on the right gear it only reaches to the pitch circle. The reason is that 3.8 millimeters is not something that applies just only when there's a rectangular area. It applies at any point. So when the tooth gets too narrow to fit fiber, it won't fit fiber. On the left side, on the larger tooth, it doesn't really do that. It allows it to go all the way. On the right side, it does. Sweet. Okay. So with sandwiching and shelling, how many layers are ideal on the top and bottom layers? So I believe our default right now, when you click fiber, I believe the default is 6 layers total, so 3 on top and 3 on bottom. That's not like ideal. Really ideal depends on the use of your part. If you only need a little bit of strength, that's fine, and that will make a part that's pretty stiff. Increasing them again increases the strength by a lot. Because as you're increasing the layers of the part, as you're increasing the number of layers, you're increasing the number of strands of fiber inside the part. See, next question. Okay, to make a stronger part, wall thickness, infill versus fiber usage, what's the difference? So when we're talking about strength on our parts, there's kind of a bifurcation. Our plastics, our white nylon is about half as strong as onyx, and then our carbon fiber is about 10 times as strong as onyx. So in terms of printing, if you're trying to get a strong part, fiber wins out every time. So someone said, for shelling, why do you mean the Z torsion not being as strong? I don't understand the term well enough. That is totally my fault for not enunciating well. What I mean is Z tension. So when you print the part, you're printing it layer by layer, and so I think we've kind of discussed this a couple times. But the reason that is because you can pull apart layers more easily than you can stretch a certain layer. Also torsion. So torsion is twisting, tension is pulling. Yeah. Oh, sorry, Alex will explain this.
Yeah. So the other part of that is that when you use concentric rings, what you're doing is, if you were to imagine the part, if you take something like our brake lever and you try to bend it around, you bend it around the axis that is like normal to the build plate, the shells will reinforce from bending in that direction. And so that's one of the advantages of shelling, is that you can reinforce around that direction in bending, whereas sandwich paneling reinforces around bending in the other directions.
There are a lot of questions here. Can the effect on the strength of a part be evaluated or simulated? Right now, no. We don't have any kind of FEA type comp for our fiber filled parts since they're composites. Um, but that's something that would be useful. The way we generally test our parts is just by printing out parts and then using ASTM standard tests to evaluate strength. But again, that's with the specific fiber fill regime. So if you filled it a different way, the part strength would be totally different. How does start rotation percent work mean? Basically, it starts from just a degree start. It starts from the top. It starts from the top and goes all the way around. It's an older feature, but basically at 0%. My understanding of how it works is at 0% you're filling your break is going to be at the top of the part, whereas at 50 it's going to be 180 degree switch and kind of all the way around. So you can scale that by 3.6 in terms of degrees. Okay. Is there a minimum radius for fiber use? Um, yes, that's a little bit trickier. But you can kind of extrapolate that same 3.8 millimeter, 2.9 millimeter loop rule. So I'd assume the radius is basically double that, so 5.8. Although I can't verify that by myself, but it's pretty easy to test. Uh, how do you set up a part in Eiger to have shell fiber orientation? So here actually, so basically, I don't think I can do an Eiger demo right now, but so basically what you do is there's two steps basically. So the first step is to put the part in with default sandwich paneling, and then make sure that those sandwich panels are working. And then the third step is in your group look, or in the grouping look that you see at the bottom of the histogram in three-dimensional view. You can select everywhere in between that sandwich panel, and you select that, and you can add fiber on the top right part of the screen. And when you add fiber, you add concentric fiber with one ring. Yeah. How much stronger is 2x concentric rings versus 4x? Is it twice as strong? Depends what metric of strength you're looking at. By like raw tension, yeah, you can imagine that it will be like since you're putting literally twice as many rings in, it'll be twice as strong. By bending or by torsion, it's harder to nail that number specifically down. When doing a sandwich fill, does it automatically do concentric fill with isotropic in between? Sandwich. So sandwich paneling, I assume you're talking about sandwich paneling. The default fill, it defaults to concentric on top and bottom. There's no isotropic in default. Is Markforged still working on getting back to plus or minus 2 thou tolerance? I think we're always working to improve our tolerances. I don't think we're at 2 thou right now. It really depends on the printer and how it's leveled, but I'd say right now we're not quite there. But in answer to your question, we're always working to get there. Let's see. How can I design a fiber path in the middle of a part without having a surface near? Is there a workaround? E.g. modeling a small gap with a 1 millimeter width? You can do fiber paths with internal hole reinforcement, which is the feature that we just launched. If you're trying to get specific paths, I guess you could do a workaround like that, although I wouldn't recommend it because sometimes when you're dealing with really small gaps, the printer doesn't perform well. I'm going to leave it to Alex to answer the questions for the next couple of minutes. I'll be back in a second.
Yeah, and just so everyone knows, we are getting a lot of questions about the whether the webinar will be shared afterwards. So if you want to come back to this information, we'll be sending out the slides, sending out the recording later on so that you can have access to this information. We also have a lot of information on our blog that we can send out along with those resources that discuss a lot of the things that were discussed in this webinar. So those links we can send out as well that contain all of this information. So a lot of you are asking about different sites and where the data will be used, where the information will be shared, and we'll be sending that out to all registrants afterwards. So just going through some of the more questions here. Um, uh, a lot of people have been asking about some of our, like, if we're planning on doing more fiber reinforcement features in the future, things like, selective feature reinforcement and stuff. And what my answer to that is that we basically, as a company, we're always working to develop better and better tools that we can give to people to help them print stronger parts. So as Daniel mentioned, just 2 weeks ago, we launched internal hole reinforcement. And so we're always developing better software, better tools to give you these reinforcement capabilities that may not be implemented now, but that will be developed in the future. Let's see, just looking through more of the questions here. Someone asks, what is the function of the reference part, which is built in the left corner when using fiber? So those of you who have our printers will notice that when you print in fiber, there's a little tower that gets built in the back left. This is essentially what we call a purge tower, and what it does is it clears off the nozzle just in case to ensure that no fiber or plastic gets sort of wiped off on the part during the print. Can I see on the printer how much nylon material I've used? That you can see that in our software. So the software will give you estimations upon material usage for both fiber and for plastics. And through those estimations, the printer and through our material usage, essentially, if you we have it set up so that when you add a new spool of fiber or of nylon, the printer will log how much material it's using so that it can give you an estimation of around when you're going to run out of fiber or plastic. And so the printer will tell you that you're running low on plastic mid-print so that you can reload in the case that you run out. We're just going to sort of focus on the fiber reinforcement strategy tips right here. I see a couple other questions on a few other topics, and so I would definitely just check out our website, check out our blog, because that's where a lot of information that both Daniel and I read a lot of the blog posts, and we put a lot of this information about tips and tricks for fiber reinforcement, for making the most of your Markforged printer. It goes on there.
Okay, so the next one is Onyx material isotropic, or are chopped fibers in the filament all laid in one direction? So there's, I think, a little bit of crosstalk here. So we do carbon fiber reinforcement in two ways. Onyx as a material is a black nylon filament with chopped carbon fiber inside of it. And so that material by itself you could describe as isotropic, although after printing it's not, because any FFF printed part is not truly isotropic in strength. The fiber that we're talking about is actually continuous carbon fiber. So when we're printing with, you can print with an Onyx. The Onyx is a thermoplastic that you can print with continuous carbon fiber inside of it. So answer to isotropic in our parts is almost always no with plastic parts. Will fiber print in a way to print between layers? Oh, you already got that one, Oz. So must the fiber reinforcement form a complete loop? I believe that we did talk about that. Yes, it does have to in some way. Can you elaborate on how a lot of fiber can cause a print failure? So it's not like a particularly complex thing. It's just that as you lay more and more fiber down, fiber is inherently very stiff. So the process that we're doing is reliable, but it's you can only get so reliable. So as you lay more and more of this stiff, springy stuff down, it's more and more likely to have a failure. And again, it's not ever. I would never say it's more likely than not you're going to have a failure, but you're kind of just increasing the risk factor. With that being said, if you're putting very little fiber in a part, if you're putting like a small or reasonable amount of fiber in a part, it's realistically almost never going to fail. A sandwich panel part is almost never going to fail, and a shelled part is almost never going to fail. A couple more detailed risk factors is if you're doing isotropic is more likely to fail, but it's most likely to fail if you're doing isotropic in a small area where the loops the zigzags are very short. So that's one thing to look out for. But generally, I would say you generally can print anything, but just be wary. why does a part have to be 100 micron using fiber? Is it ever going to be 200 to speed things up? So three of our fibers actually require 100: fiberglass, Kevlar, and HSHT. Carbon fiber actually requires 125 micron. The reason for that is that's the size of the fiber. We don't ever comment on our specific roadmap, but what we can say is that variable fiber is something that's been requested a lot, so our varying layer heights, and it's definitely something that is possible to do. So ideally in the future, maybe something along those lines. So, can you explain what the percentage of triangular infill means? So the percentage is a little bit of a misnomer, but basically what it is it's the amount of fill with triangles. It's with triangles, it's kind of harder to when you have 100% triangular infill, there's still going to be holes in the part. But on like a very macro perspective, it's two bounding box. It's a kind of a bounding box that we've set of size of triangles that we know will work, and 1% infill is the largest triangles we know will work, and 100 is the smallest. With rectangular, if you set your fill to rectangular instead of triangular, and you set it to 100%, you can get an actually solid part. But we don't usually recommend that, just because with thermal gradients, it makes parts more likely to warp if they're full fill. Is the minimum wall thickness that can have a fiber dependent on wall layers? We generally advise that you keep the default number of wall layers when you're printing, especially with fibers. So I'm going to say no. It is just the minimum. Let's see.
So we're also getting a lot of people with very specific applications in mind. Because we can't quite get all the information from you via our questions portal. If you're laying out a part or you have questions about laying out a part, you can always submit a support ticket with the link to that part and ask about fiber routing, and that will get directed to one of us, so we'll be able to help you set up your part for your specific application.
Is placing multiple layers of fiber still a way to combat warping? Yes. We did a webinar. We definitely have done blog posts, and I believe we did webinars about printing and warping. And yeah, so there's a number of ways to combat warping. Some of them are filleting, some of them are using onyx as opposed to nylon. But yeah, one of them is definitely putting fiber in, because that fiber will give you an inherent stiffness that will combat that shrinking force that contributes to warping. How many roof or floor layers to get a smooth surface finish? Generally stay with the default. Don't go below it. Depending on what machine you have and what layer thickness you have, it'll adjust the number. But there is a specific, like, if you go below what we kind of put in our defaults, we don't guarantee a good surface finish. Which is more efficient in printing time? So there's one that says, which is more efficient in printing time? Example, rectangular arm like a bike crank to do X bracing that the fiber follows, or to do striping that would lay sheets and levels through the X-axis. So it comes down to like the length of the fiber you have to lay. I'm not exactly sure what you mean by X bracing, do you mean by cutting out the part and doing forcing the fiber to do cross bracing? I would say generally the most efficient time-wise to get the most strength is generally shelling parts. But striping does also have its benefits. So striping is of a similar speed because it turns out adding a few layers that are filled in the middle of the part is about the same amount of time as adding a bunch of layers that only have very little fiber in a part. There's another question about how many layers it's ideal to sandwich panel apart. I think we discussed that question before. It really depends on the strength you need for a part. That's one we just answered. Is there... Sorry, we're looking at more questions. Alex, do you have more? All right. Okay, so we have another one. If you would print a strong part like a jig part for pipe bending, how would you think about the amount of plastic material? So plastic doesn't explicitly contribute to strength. If you're putting fiber and plastic in a part, the strength of the plastic is relatively inconsequential in terms of the strength of the fiber. But generally, I mean, the plastic is just it's similar to a strong thermoplastic, and then the more of it, the less likely it is to bend. What the sharp angles one? So when can fibers break if they're placed in sharp angles? So generally, our software will not allow the fiber to do anything to put it in a scenario where it will break. The example is that is isotropic. Our fiber can lay down in isotropic patterns, which are as tight of a radius as you could pretty much imagine. But yeah, I would say you don't worry about the fibers snapping within parts. Will Onyx absorb moisture from the air after prints? Generally, yeah, nylon it has the capacity to absorb, but it will not harm the part. We have not done a ton of research on how our plastics change after printing, but it's something that we'd like to do. All right, I think that's all the questions we're going to answer for now. If you have any more questions, feel free to send them to marketing@markforged.com, and we'll see if we can get to them as the application engineers. And if you didn't get to catch all of this, or you didn't make all of it, or you're looking for other things, we'll be uploading a video of this webinar that we'll then send to YouTube as an unlisted video that we can send out to you as a link so that you can view this at your later convenience. Thanks everyone for turning out. Hopefully you learned a lot about this stuff today. Thanks.